Hello, hi, I'm Yuval, and I'm going to present work that I'm doing together with Huming Chan on enhancing the bug notification system that we have in the Redis gateway in Ceph, so it fits better into the serverless computing world. So first, I'm going to give a quick overview on what we have with regard to bug notifications on the Redis gateway. Then I'm going to show some issues and some scenarios in which this might not be sufficient. And then I'm going to present the new offering that we're going to have in the Redis gateway that fits better into some of the serverless computing scenarios. So let's see first what we have. Bug notifications, what it does. So bug notification is all about sending out information from the Redis gateway, from the object front end of Ceph into external systems. So anytime you make a change to an object, we want to be able to notify that to some other applications. What they do with that is something that it's up to them. But the important thing is that we notify them because this is the enabler for many interesting use cases and functionalities that we're going to show later. What are the compounds and building blocks of bug notification? The first thing is a topic. So the concept of the topic is this is an aggregation point to which the events and the modifications are being published to. And it points to an endpoint. The endpoint could be a variety of endpoints. We have Kafka endpoints, AMQP endpoints, HTTP endpoints, and so we're going to even have AWS SNS and AWS Lambda endpoints. And the other side of the endpoint of the topic is the notification. Notification is a definition that ties together a topic, which is what we said is an endpoint, together with a bucket. And this tying together is done based on filtering. So we say, let's say we have a Kafka topic that points to a specific broker and to a specific topic on this Kafka broker. And we have a bucket that we want to track changes on. And we say, okay, let's define a filter. So only a subset of the changes of the bucket, let's say only creations, only copies. Maybe the filtering could be based on object names. It could be based on prefix, suffix, a regular expression, or even tags and attributes of those objects. So this combination of tying together a topic with a bucket together with filtering, this is what gives us a notification. We're sending over those notifications as events, and those are S3 compatible events using some JSON schema for any application to consume in a way that is easy for them because it's based on something that they might already know from the S3 world. Same with the configuration, all the setup, it's all REST-based, it's all AWS compatible REST API. So the tooling is already there if you're using Boda3 for Python or some other tool set to integrate with AWS, you can use the same tool set to integrate with our solution. So this is really in a nutshell what we currently offer. Let's dig a little deeper into that. So we have here on the side, we have the Ceph system. And we're talking about the S3 frontend on the object frontend of Ceph. And this is the Redis gateway or the RGW. If you configure bug notification there, then anytime, according to whatever configuration that you give, anytime a change is made to an object of a specific bucket, a notification is going to be sent to the topic that you configured. The topic in this case could be a Kafka message bus. And well, this is just a channel, just a message bus, but you can have something else on the other side of the message bus that consumes those notifications from the message bus, subscribe to them. And this could be, for example, a Knative serverless function. And this actually does the work. So on one hand, we have Ceph sending out notification. In the middle, we have a message broker. In this case, Kafka. It could be AMQP. It could be AWS SNS. And on the other side, we have something that consumes the messages. In this case, it's a serverless function. So this is currently offering. This is what we call a push mode. Push mode because Ceph is pushing, or RGW is pushing notifications from it into the message bus, and then it's up to whoever set up the message bus and the consuming applications to continue and take it from there. These are actually real life examples that we have for that. One example is coming from the financial world. So this showed the power of bucket notifications for an application in the financial world to synchronize information between different entities. In this case, different banks. Those are different entities. They're not coordinated in any sense. But bucket notifications allows us, or allows the application to create an interface between them that is loosely coupled. So notifications are sent whenever something is. So this is, for example, like a payment process where you move payment from one bank to another bank. So you don't want to create complex APIs between the two banks, or APIs that has limitations on scale and different scaling of the different banks, because those are two different entities. It's difficult to synchronize them. So this is where bucket notifications come into play. Whenever something is changed in one bank, payment is made, an object is uploaded, notifications is sent. When the notification is sent, there's some external processing system that knows that something needs to be updated in the other bank. But because this is not a direct API between the two banks, then the scaling could be different. If one bank has more machines, the other one has less, and so on. And because it's all based on those standard notifications, the integration point is the only place that needs to know about the two different places, and you don't need to manage different APIs between different actual entities. Another example that we have here, completely different, but using the same push mode bucket notification, is coming from the medical world. So the problem that we have here is that researchers want to get as many as X-rays or chest X-rays, in this case, to research pneumonia. There's lots of X-rays being uploaded for medical reasons into the clinic, but you can't just use them for research. The privacy issues, and most of them are not adequate for research and so on. So this is where bucket notification comes into play. Here we present a system whenever you upload a chest X-ray into the patient's information, which is the clinic's bucket, there's a notification being sent to a Kafka message bus that triggers a Knative serverless function. This function wakes up, reads the image, and does a couple of things. First of all, it sees if this is an interesting image. It could be that it applies some AI to have an initial screening to say if there's a potential for pneumonia in this image. If there is a potential, then it does two things. First of all, it puts this information into the image and writes it back into the patient's bucket, for the doctor to have a look and maybe have a priority to examine this patient. But it does another thing. It takes this image, it strips off any personal information out of the image. The information could be either in the metadata of the image, or the information could even be on the image itself, like the name of the patient or some ID number. And once it strips off and anonymizes the image, and if this is an image that is suspected to be of interest for research, it uploads the same image into the research bucket. So for the researchers to have those images later on to be used for their work. So this is an automatic system that ties the medical system with the research system and allows for lots of information to be at the disposal of the researchers, while doing everything manually between two different departments and so on would have been very difficult, especially with the privacy concerns of such a system. So these are two examples where we use bucket notifications. We use them in push mode. This is what we already have, and we're using some kind of a broker mechanism, Kafka in this case, to associate the bucket notification pushes being pushed into it with the execution of the serverless functions, in this case, Knative ones. So what is wrong? Well, you can push directly bucket notification into the serverless function. You can do that by invoking an AWS Lambda function, or by directly invoking a Knative function. The problem is that this only works for very simple cases. It doesn't scale well because you need to make sure that you send those and you have enough recipients on the other side. Um, Although some of the serverless frameworks do take care of that, um, and you can't wait for the serverless function to finish their work. So sometimes what they do, like say if you look at the medical imaging case, it takes them a while to actually do the processing and everything of the images. And you can't really block and wait for that to end. So you send over the notification, and then they go on and do in their own time asynchronously their work. But if they crash in the middle of something wrong happened, then the notification is lost, and you don't know about that. This is why this direct native communication with the serverless functions is problematic. A way to solve that is that you put actually this kind of functionality into the message broker, saying, you're going to put stuff in the message broker. The message broker is persistent. It has all kind of mechanisms to make sure things are not lost. And on top of that, you can even have a system there saying that event is deleted from it only explicitly once the serverless function finishes their work, and it can manage retries and everything. This is a good solution, but you need this message broker to be introduced. If you already have that, the message broker, then this is great. And this is the case in many cases. This is why this is a good solution. If you don't have that already, then introducing a message broker for the sake of those systems is a heavy task. Introducing, especially something like a Kafka message bus for large-scale system is a work task by itself. And you also need to expose that so that the messages can go into it. So you need to define the firewalls and security issues and so on and so forth. Looking at all those things, we want to introduce another solution here. And this solution would be pull mode. In this case, we would be a kind of a message broker, and we will have a message queue APIs that would allow external system to actually fetch the information from us. Quite similarly to the way that they fetch the information from the external message broker. Um, this would be a good solution to mitigate the problems that we've just described. We can summarize saying that if the message broker is something external to us, it does the work. It takes care of the persistency, things are being fetched from it, and so on. And the only thing that we do is push into it. If we are the quote unquote message broker, then we do the persistency, which is not something very complex for us because we have a persistent storage. This is what Ceph is all about, right? So we use Raiders for persistency, and when we add the mechanism that allows the applications to fetch information from us and let us know when they finish processing so we can dump them and throw them away, and also have a mechanism that allows them to retry stuff if they crash in the middle and so on. Now, the next phase, we'll see in more details how we do that. So this is the pull mode. This is something that is currently in process. So the receivers for those pull mode, or one of the options that we want to integrate with, is something called KEDA. KEDA is a system that's saying, okay, we have a problem that we want to fetch information and do some lengthy and heavyweight processing on it. We need to have a mechanism that knows how to tell us how to scale, because we need to know how many work we have waiting in the message queue, in the queue. And we also need a mechanism that tells us how to retries and so on. So all this is in this system called KEDA. It's a serverless function, a lightweight serverless function, but unlike Knative, it's not a messaging-based serverless function. It is the only thing this serverless function is doing is checking how much work there is in the queue, and then scales the workers according to that. So you have something called a scaler. It just looks at the length of the queue of the system that you read information from, and according to that, it scales more and more workers that go on, fetch stuff from the queue, do their work, and then tell the queue that they're done. For that to work fine, or for that to work properly, we need something inside Redis gateway that addresses those requirements. So we took the idea from the AWS SQS API, and we don't provide a full message broker. This is not what Ceph is about. But we follow those ideas because first, they're good for KEDA. I mean, they fulfill their functionalities. But not only that, we try to support the same APIs because, again, tooling would be easier. If you have a tool set that knows how to talk to AWS SQS, then with only minor modifications, you can use the same tool set, the same SDK, and so on your application to talk to our system. Storage has to be durable, but as I said, this is easy for us because we're a Ceph. We have durable storage, we have scalable storage. All these problems is good are solved for us. We co-locate most of the processing inside what we call the OSD. The daemons running co-located with the storage for better performance. And as I said, we're not building at least for now, we're not building a full-fledged message broker based on Ceph. We're just trying to mitigate the gaps that we have for bug identification by introducing this pool mode. How do we achieve those things? So Redis gives us the durability and scalability for actually the length of the FIFO. So the queue could be as large as we want, as notifications are being added to the queue. I mean, the queue is also being drained, but we have almost no limit on the size of the queue because this is based on Ceph, on Redis. And of course, everything is durable and persistent because this is Ceph. We write to the queue synchronously from the Redis gateway. So processing would be asynchronous. It could take a long time. You take the image, you run some AI on it, you do whatever. But just pushing into the queue would be synchronous from the Redis gateway, so that we're kind of fail tolerance in the sense that if we failed, everything failed atomically. And writing to the queue is not a big deal. You just write some metadata on the object that you just uploaded or modified. And this is only a chunk piece of information that you write into this queue, which is also a Redis object. And the queue usually sits on fast media, so performance should be okay. The Redis gateways also have their availability and scale characteristics because you have multiple of them. They're stateless. If one crashed, another one takes over. And it doesn't really matter to which Redis gateway you talk to. Notification will be written to the same queue object or that we use here. And because there is some limitation on the amount of writes and read that you can do concurrently from a single FIFO, then you can have as many of them as you want in order to have a better performance or more scalable solution. Now, on the other hand, there is those workers that actually does the processing. So what do we support there? We have an at least once guarantee, which means there could be duplicate notifications if there are failures. On the regular processing, there shouldn't be any duplication, but in case of failure, there might be a case where we're not sure whether we have sent notifications or not, or we're not sure whether the worker processed it or not, and for that, there could be duplicates. Multiple clients can read from the same FIFO, so whenever something is being read from the FIFO, it's being marked as being read, and therefore another client can go and read from the FIFO and would not read the same thing that the first client just read. Client trim the entries explicitly when they're done processing them. This actually guarantees that if the client crashed and didn't finish the processing, it would not trim it. So after some timeout, what we call the visibility timeout, if something is not trimmed, and it will appear again, and another client could read it again. So this would be like the retry mechanism. So clients can retry stuff that other clients started processing but died in the middle. Things that have been read but not trimmed, eventually deleted after some retention period, just to make sure that the queue doesn't build up with endless messages over time. This is a quick example for the visibility timeout. So here we have a client that takes 5 elements from the queue. The other client doesn't see those 5. So when another client, completely uncorrelated with the first one, read another 3 elements from the queue, it would read the next 3, and so on and so forth. The next client won't see all the first eight elements from the queue and would continue with that. And this is how it works. Now, lastly, I'm going to show how the visibility timeouts work. So when client finishes processing, it trims the queue and deletes those entries. Another client streams the queue and delete the another set of entries. And then other clients read and delete those entries. If a client dies and crash in the middle, then those entries, they're never going to trim them. And after the visibility timeout expires, they're not going to be invisible anymore. They're going to be visible. So the next client that's going to read from the queue can reread them again and process them. This was really, in a nutshell, the mechanism for the visibility timeout and the trimming of the queue that allows for multiple clients to process the queue within at least one guarantee. This is the presentation of what we're going to add to the bucket notifications. If you have any questions for women or for myself, please don't hesitate to contact us. Thank you very much and see you.